Meet Marcus. He just found out that the distance from Earth to the Sun is about 93 million miles. He tried writing it on his homework paper and nearly ran out of space. There has to be a better way, right? Well, today we're unlocking a superpower that scientists, astronomers, and mathematicians use every single day: scientific notation. By the end of this video, Marcus and you will write enormous numbers in seconds. Let's go! Before we get to scientific notation, we need to talk about powers of 10, the building blocks. When we write 10 to the first power, that's just 10. 10 to the second power, that's 10 times 10, which equals 100. 10 to the third power, 10 times 10 times 10 equals 1,000. Here's the coolest shortcut. The exponent tells you exactly how many zeros are in the answer. 10 to the sixth power, that's a 1 followed by 6 zeros, 1 million. Pretty neat, right? Here's the problem Marcus ran into. The distance to the Sun is 93 million miles. The number of stars in the Milky Way galaxy? About 300 billion. That's 300 billion. And on the tiny side, a single bacterium is about 0.000001 meters wide. Writing all those zeros is exhausting and easy to mess up. Scientists needed a smarter system, and that's exactly what scientific notation gives us: a clean, compact way to handle extreme numbers without losing your mind. Here's the formula for scientific notation. Every number in scientific notation looks like this: a times 10 to the power of n. The rules? First, a must be a number that's at least 1 but less than 10, so things like 3.5 or 7 or 1.08, all good. Second, n is your exponent, a whole number. Positive exponents mean big numbers. Negative exponents mean tiny numbers, less than 1. Think of it as dialing a number up or down in size by moving the decimal point. Marcus is starting to see it now. Okay, here's the game plan for converting any big number into scientific notation. Step 1, place the decimal point right after the very first non-zero digit. Step 2, count how many places the decimal moved to get there. Step 3, that count becomes your exponent. If the number was big and you move the decimal left, the exponent is positive. And step 4, write it in the form a times 10 to the n. 4 steps. That's all it takes. Ready to see it in action? Let's solve Marcus's original problem, 93 million miles. Step 1, place the decimal after the first non-zero digit. That gives us 9.3. Step 2, count how many places the decimal jumped. Starting from after the 3, we move left past 7 digits. 1, 2, 3, 4, 5, 6, 7. So we moved 7 places. Step 3, our exponent is 7. Step 4, we write 9.3 times 10 to the power of 7. That's it. 93 million equals 9.3 times 10 to the 7th. Marcus's homework just got a whole lot neater. 300 billion stars in the Milky Way. Step 1, place the decimal after the first non-zero digit. That gives us 3.0. Step 2, count the places. From after the 3, we move the decimal left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We moved 11 places. Step 3, exponent is 11. Step 4, we write 3.0 times 10 to the 11th, or just 3 times 10 to the 11th. 300 billion written in just a few characters. That is seriously powerful. Now here's where it gets really interesting. Tiny numbers. When a number is less than 1, like a bacterium's width of 0.000001 meters, we use negative exponents. Instead of moving the decimal left, we move it right until we get a number between 1 and 10. Each step to the right makes our exponent more negative. Super important. A negative exponent does not mean the number is negative. It just means the number is really, really small. This tricks a lot of people up, so remember that. Let's write the bacterium size, 0.000001 meters, in scientific notation. Step 1. Find the first non-zero digit. That's the 1 all the way at the end. Place the decimal right after it, giving us 1.0. Step 2. Count how many places the decimal moved to the right. 1, 2, 3, 4, 5, 6. We moved 6 places to the right. Step 3. Because we moved right, our exponent is -6. Step 4. The answer is 1 times 10 to the -6th. That tiny bacterium, 1 times 10 to the -6th meters. Science is so cool. Now let's go the other direction, from scientific notation back to standard form. Say you see 4.7 times 10 to the 4th. How do you expand that? Your exponent is +4, so move the decimal point 4 places to the right. Starting at 4.7, move the decimal right once, 47, twice, 470, 3 times, 4,700, 4 times, 47,000. So 4.7 times 10 to the 4th equals 47,000. Marcus just tried this on his own and nailed it. Going both directions, that's true scientific notation mastery. Here's a bonus skill, comparing numbers in scientific notation. Which is bigger, 3.2 times 10 to the 8th or 9.1 times 10 to the 7th? First, look at the exponents. 8 is bigger than 7, so 3.2 times 10 to the 8th is the larger number. Let's verify. 3.2 times 10 to the 8th equals 320,000. That's 320 million. And 9.1 times 10 to the 7th equals 91 million. That's 91 million. Yep, 320 million beats 91 million. When comparing, always check the exponent first. Bigger exponent, bigger number. Before we wrap up, here's your quick cheat sheet. If you're converting a big number, 1 bigger than 10, your exponent will always be positive. If you're converting a tiny number, 1 smaller than 1, your exponent will be negative. The first part of your scientific notation, the a value, always has exactly 1 non-zero digit before the decimal point. And remember, the exponent always tells you how many places the decimal moved. Pin this to your brain and you'll never get confused. Remember Marcus at the start, staring at 93,000 and wondering how to fit it on his paper? Now he writes it as 9.3 times 10 to the 7th without even blinking. From the distance to the sun to the size of a bacterium, scientific notation handles it all. You've got 4 killer skills now: understanding powers of 10, converting big numbers, converting tiny numbers, and comparing them. You think like a scientist. Keep practicing, and these will feel totally natural. You've absolutely got this.